I am BABU, working as Associate Professor in CSE department. So I am going to give a lecture based on the computer network subject. So there I am going to give a topic on error detection and error correction. So what it is, what an error and how it can be occurred in the computer network. So let us see a simple diagram how it transfers data. So suppose we have two computers, computer A, host A and host B. So these two computers or systems can be transfer the data or message from one computer to another computer. So which system sends the data or message, that it is called a sender, and which computer receives the data, that it is called a receiver. So these two computers communicate with the channel or medium. So this is called a medium. So this is nothing but the cables, digital cables, what the signals carried from one end to the other end. So during that time, these cables carried signals like digital signals 1, 0, 0, 1, so like a bit streams. Bit streams. So when the sender sends a packet or message from one end to the other end, that is receiver, so it carries by the channel or cable and it received by the other system, that is a host B. So while receiving this message, whether it is correct or not, we are unaware of that. So the sender unaware of that. So because of that, it is required some analysis, so whether the received message is correct or not, or the message has any error or not. So how it is possible, while the medium carries the signal, how it is possible to make the errors or modify the messages? So this question that may arise. So the reason is that when it carries, the medium or cables can be affected or interfered with the other electrical signals. Suppose for this medium you have any cables along with that, so that cables interference, signal interference may be affected, and also due to other environmental factors and technical issues, the message can be disturbed. So that disturbed message, it has an error, so that it is called a exception or error in the computer networks. So it has. Suppose if the receiver receives the error message, it can be dropped by the receiver, then there is no exact transmission or communication happen by the systems or networks. Then what happen? If you want to make a reliable communication, that is the successful communication, successful transmission, the receiver must verify the original data and also detect the errors. If possible, we can correct the errors. So the error may be unknown or known errors. If it is the known errors, the system intimate to the center or the network medium. So this type of error occur, please adjust yourself. So this kind of packets or beacon frames or testing packets sent back to the medium or a center. If it is the known errors. Unknown errors, so how it is happen? So unknown errors based on the interference. So there when these bit streams passed over or transmit over the medium, so the 0 can be transmitted to 1 or 1 can be interchanged to 0. So the interchanging of bits can be changed the message content. For example, I am sending here world is a message. So each letter has a byte, it is converted to the bit streams, and when it is transferred to, if it is 1001, it changed 1011, automatically instead of the W it can be changed S. then the message can be changed. Instead of the word, it is sold. So this kind of error is possible because when it is a bit changed inside this medium, or when the receiver receives this kind of information. So what type of errors it can be occur? So whether the bit can be changed or interchanged, in the sense whether a single bit or multiple bit. So what we have? So there will be two categories for that: single bit errors and burst errors. So burst error in the sense distance, that is length, the number of bits increased, that is more than one. So when one bit is interchanged, instead of 0 to 1 or 1 to 0, this is called a single bit error. So when we have the two bits are interchanged, 1 0 1 0. So this 0 interchanged as 1, this 1 interchanged as 0. So two bits are interchanged. This it will be called a burst errors. So error length is 2. Two bits interchanged. So this is the basic idea how we can identify errors in the computer network transmission. So this is a single bit error. 0 is interchanged to 1 from sender to receiver. So this is the multiple bits. So here I am saying the consecutive 2 bits. So one other question may be raised, sir, whether it is only the consecutive bits can be changed or randomly it can be made the errors. So both it is possible. Consecutive bits or random bits can be affected. So when a message consists more than one bit error, that it is called a burst error. So here is the another example for the burst error. Consecutive 2 bits are interchanged here and the random bit also interchanged here. So both possibilities viable. So two kind of errors, single bit error and multi-bit error, that is burst error. Okay, so error occurred in the message. How can we detect, sir, whether it is any techniques or possibilities are available or not? So how we can detect the errors? What are the methods available onto this case? So there is the simple scheme we have, that is the classification to identify the errors in the computer transmission. So what are the classification? That is the categorization. So first we can use the technique as parity bit. So using this technique we can identify. So what is this? We can add a redundant bit for the concerned original data. So through that we can identify the error. We'll discuss what's that. So with this technique also we can identify this category. This technique also classified two other sub techniques, sub classification, VRC and LRC. Then the next technique is CRC, cyclic redundancy check. So this is the most powerful technique to find the errors or detect the errors. And the last one is the checksum, which is mainly used for internet transmissions. So the name, the alternate name for this terminology is internet checksum, also we can use it for this. So that kind of importance given for the internet transmission to find the errors or detect the errors in the internet transmission. Okay, so among this, first we are going to discuss the parity bit technique. So the parity bit technique has two things. One is one dimensional, that is one bit parity technique, and two dimensional, that is more than one bit. Two dimensional is more than one bit, that is rows and columns, like a matrix, rows and columns used for that. So there we can find the number of errors detected in this checksum or data. So here the first one is single bit error, that is simple parity check. Simple parity check. So only one bit, parity bit is introduced With that we can identify the errors. So you can ask the other question here, sir, we are using the error detection technique using the parity bit. So whether the VRC support for only 1 bit error or it can be used for finding the burst error also. But efficiency of this VRC, that is simple parity check. So this is mainly an efficiency for single bit error. But it is also possible to find the burst errors, but the accuracy as well as the efficiency is somewhat less than the other techniques. So concerned to this simple parity check, this is called the vertical redundancy check. Vertical redundancy check, VRC. So what's the technique followed here itself? So there the bit streams are there 1 0 1 0 0 0 1 1 1 0. So likewise the bit stream is available, it's a message. So from that bit stream you can fix n number of bits as a original data unit. Original data unit. So for example, I am fixing n is equal to 7. It means that 1, 2, 3, 4, 5, 6, 7. So this 7 bits concern to a single data unit, that is original data units 1 0 1 0 0 0 1. So here in this data unit you add a 1 bit, that it is called a parity bit. So how can you add this parity bit? In what method you are using for that? So for that only we have the other two things, even parity and add parity. So what is even parity? That is total number of ones in the data unit becomes even. So count the number of ones available in here 1, 2, 3. So 3 ones are available. If you are using the even parity method or even parity technique here, you can add 1 bit is a 1. It means that the counting of number of ones is even. So 1, 2, 3, 4. So 4 number of ones available now. So now we created a parity bit using even parity. Suppose if you are using the add parity is individual, number of ones is add, that is 1, 3, 5, 7. So the count should be like that. So here we count the number of ones 1, 2, 3. So already in add, so we can make it as a 0. So this is the parity bit. So parity bit is 0. So now combine this original data unit as well as this bit. So both combine together and make it as a unit. So this is called a single data unit added with the parity bit. So if it is added with 0, so this technique use the add parity. When you are adding here 1, it will be the even parity. So how the sender and receiver can react with this technique? Because earlier I said the sender transmits the messages and receiver receives the message. In both sides the analysis should be happen. So that it is called how the parity bit is generated here and added to the data unit, and while receiving by the receiver, how it can be analyzed and detached the parity bit from the original data unit, and how this original data unit can be accepted by the receiver. So this can be discussed in what technique or what method we are using here, that is given. So here the center node, it is called generator, that is parity bit generator. When the receiver side we have, it is checker. So center generate the parity bit, receiver check the parity bit. So generator and receiver, these two terminologies used. So here the center node generate the parity bit. So original data is given 1 1 0 0 0 0 1 is the original data units given, and calculate the parity bit. So here the downwards we are giving, it is even parity check used here. So count the number of ones. So in the original data unit the number of ones is 3. So generate the parity bit along with that, that is the other one is you can add it to make a even number. So 1 is a parity bit is generated by the center node. So that combined together make a one single data unit, so that it is transmitted through the transmission medium. While receiving by this receiver, so this signal converted to the bits and count the number of ones. Count the number of ones received data unit. So whether it is even number of ones, even parity is okay, what it is received here. If there is add number of ones is there, so it can be easily identified is there some error is detected. So that it is here checked even. So if it is even, we are drop the parity bit and accept the original data. Drop the parity bit and accept the original data. And if it is not even, automatically the data can be dropped, that is reject the data. The receiver node reject the data. So this is a simple process. It can be used both sender and receiver to generate and check the error process. So generator and checker both is used for error detection schemes. So this is explained for vertical redundancy check VRC method. Okay, so that it is for first technique. Then second technique, LRC. So the other example is given here for add parity. Number of ones should be add number. Right. So the other technique, second technique is LRC. That is two-dimensional parity bit check or error detection scheme. So that is called longitudinal redundancy check. LRC is the longitudinal redundancy check. So this can be used rows and columns. Rows and columns like tables. So that the data units are created, original data units 1 1 0 0 1 0 1, then 1 0 0 1 1 1 0. So likewise continuously we have number of rows on the data unit. So for this you have to generate the parity bit. So here 1 1 0 0 1 0 1. So if we are using the even parity, number of ones are 4, that is even. So you can generate a parity bit as a 0. Then 1 1 1 1. Again the second data unit counting, the number of ones is 4, even number. So generate a parity bit as a 0. Then here also you can generate a parity data unit. Parity data unit. So count the number of ones here also. If it is even parity 1 1, number of 1 is 2, generate 0. Then 1 0 1, 0 0, then 0, 0 1 1, 1 1 0, 0 1 1, 1 0 1. So make a number of ones are even. So this is parity data unit. So the vertical also we can compute this, and also for parity bit also we can generate a parity bit. For parity bit also we can generate parity bit 0 0, so 0. And now this can be connected with each data unit, and this can be transmitted one by one. This can be transmitted one by one, and receiver receives and check again the similar process what so far we discussed, the generator and checker process for VRC schemes. So that it is given for the error detection schemes. So adds additional character So here the send message is a data message. For that you are creating a data unit. So for D we have 1000 then A 10000001. For T we have 1010100. For A we have 1000001. So this is the original data unit what we have. For this we need to generate a parity bit. So for each data unit we have parity bit is 1101. So what here I explained, this parity bit has to be generated. According to that, the parallel count, the parity data unit also has to be generated. So here its number of ones are 4, that's odd parity is used. Add parity is used. So 4 ones here making the 5, we are using 1 here. Then all are 0, we are using 1 here. Then we are only 1 is there, so 0. Then 1. So likewise, what it is there, based on that, making the add parity, we are using like that. So the parity data unit also created here. Then, so this is the another division. This parity bit is created for this parity data unit, as well as it is from the parity bit collections. So 1101. So make it as a 1. So here it is used that. What it is here we have, this is used. So all this make a, so this kind of data units, individual data units, and it can be transferred one by one. It can be transferred one by one, and receiver receives this data units and verify once again whether the add parity is available or not. So if it is there, then there is no problem, it can be accepted, otherwise it is rejected. So generator and checker, both it can be work everywhere, the sender and receiver process. So what is the performance of this? So this kind of multiple data unit, that is rows and columns error, 2-dimensional or LRC, whatever the terminology we are using, this is mainly used for detecting all burst errors up to length n. If the 2 bits in one data unit are damaged and 2 bits in exactly same positions in another data unit are also damaged, the checker will not detect the error. So this is the another issue we have in this. This is the issue we have, that is drawback in this technique. So once the 2 bits in one data unit are damaged, so that is the problem to identify, because it can be matched with this. For example, so here we generate the 0 here, so here it can be converted to 110110. 2 bits are interchanged here. 2 bits are interchanged here. So this can be, now it can be add number, we can put a 0 automatically. So its count, if we are using the add parity, the count even parity, if count is matched, so there is no data error in the sense, but actually the 2 bits are interchanged. So this is one kind of error we are occurring. And also the exactly same position in another data unit are also damaged. For example, here we have 0 0, so it is changed as 1, so this is changed as 0. So the same position in 2 single data unit, that also cannot be find the error in this. So this is the issue we have in this. So this can be overcome, this drawback can be overcome using the other technique, that is CRC, cyclic redundancy check. So what is this? So what so far we are using, everything is based on the parity kind, add parity or even parity, and also we are performing the addition. So this is the kind of things we are using here, the simple things to find the errors or detect the errors. So the next thing, instead of the addition, we are using the binary division method. Instead of the addition, we are using binary division method. So this is called modulo n division. This binary division named as modulo n division method. So here the sequence of redundant bits called CRC or CRC remainder. It means that whatever the bits we have 0 0 1 0 1, if it is the message, so this can be generated with the generator, and we have one other thing is a divisor. So this divisor may be 0 0 1, so you can make a modulo 2 division here because binary division. So modulo 2 division. So we can perform 1 0 0 1. So here we can perform the XOR operation. We can perform XOR operation. So XOR operation in the sense, if it is both are the same bits, it can be generated as a 0. So when we have the different bits, it can be generated as a 1. It means that where we have 0 0, it can be generated 0. Where we have 0 1, it can be generated 1. Where we have 1 0, it can be generated as 1. Where we have 1 1, it can be generated as 0. So this is the XOR operation that you have studied in your digital principles paper. So that kind of operations you are performing here itself. So while performing all these units, what you are getting the final remainder value, so that it is called a CRC remainder. So that it says here CRC or CRC remainder. So that it is appended to the data unit. So this remainder value can be added to this original message while transmitting from center to the receiver. So that it is appended to the data unit, so that the resulting data unit becomes divisible by a predetermined binary number. Becomes divisible by a predetermined binary number. So that it says here. At the receiver side, okay, the center side you are generating CRC remainder and added to the original message and transmitted to the receiver through the medium. So receiver side, what kind of checking process it happened? So at the receiver side, the incoming data unit is divided by the same predetermined number. So if there is no remainder, the data unit is accepted. It means that, so what the CRC remainder is added here. So for example 001 is generated here. So this can be added 001. So this is the CRC remainder. CRC remainder. So this can be again perform the modulo 2 division in the receiver side also using this predefined divisor value. Predefined divisor value. So while performing this division, it can be received the remainder as 0. Remainder as 0. So that it is says if there is no remainder. No remainder in the sense remainder should be the 0. If it is 0, the received message is the original message, original data unit. You can accept that. So the data unit is accepted. Suppose if there is any remainder, instead of the 0, I have 0 1 0. If there is any remainder, the original data unit get damaged or it made errors. The message, errored message. So that time this message can be dropped. So this is if there is a remainder, the receiver indicates that the data unit has been damaged during transmission. So this damaged message can be dropped or rejected. So this is can be explained with the pictorial manner. The receiver side and center side both we have. The center side, the data. So along with the original data, as per the CRC generator rule, the at last of the message, the succeeding 3 number of zeros, that is n minus 1 number of zeros can be added at the end of the message. So what is a n? So this n can be computed from the predefined divisor. Predefined divisor. So what is the number of bit the divisor has? Suppose if it is the 4 minus 1, 3 zeros we can be add. If it is the 3, for example, here we have only 1, 2, 3, 3 bits are there. So n is equal to 3. So n minus 1, 3 minus 1 is equal to 2 zeros. So you need to add 2 zeros at the end of the message unit. So that it says in the center side data, comma 00.00, that is n bits. So here it takes this n is from the computation of n minus 1, that it is from the divisor. So you can add it this. So this is combined together, you can make a message. You can be make a message. Then after that, divisor. So divisor is n plus 1 bits. So as per this computation, it says n number of zeros and n plus 1 number of bits in the divisor. But we are computing the number of zeros from this because we have the predefined number. So that I am taking the different computation, make this instead of the n plus 1, make a n bits here, and instead of the n number of 0, n minus 1 number of 0. So this as a student mentality you can easily identify, because it can be make the confusion n number of zeros. Suppose I am adding 5 number of zeros here, then the divisor should be n plus 1, 5 plus 1, 6, but already predefined divisor we have only the 3 bits. So this type of confusions may arise for the student mentality. So that we are fixing this, first take a divisor and make you n number of bits is here and count the number of bits. So n is equal to 3 and add n minus 1 number of zeros here. So this is a sequence way you can easily understand. Okay, don't confuse with that. So what you said like this, what you have this. So that is the technicians. Technicians we can easily understand, but as a student I cannot understand, because I can make an argument. What I said here, 5 zeros I am adding, sir. Why don't you use the 6 bits as this? But it is a predefined. Divisor is a predefined. We have only 001. So this type of unnecessary arguments may rise because of this simple queries. So that's why I am taking this n is here and n minus 1 zeros you have to add. Okay, so let you understand this. So after this, so divisor is available, original message is available, and perform the modulo 2 division here. So after performing the modulo 2 division, we have the remainder here. So that remainder, it should be added to the original message, so that it is called CRC. That it is called CRC. So I will show the example that you can easily understand. The next we are going to discuss the example that you can easily understand what it is, how we can generate. So this is the center side detail. So along with the original data, CRC is combined together and transmitted to the medium, and the receiver receives this data as well as CRC, both it is received, and perform the checker, CRC checker. So the receiver performs the CRC checker. So CRC checker receives the CRC data with CRC, and it performs again the modulo 2 division, that is the binary division, and find the remainder. If the remainder is 0, the data is a original data unit, you can accept. Otherwise, if it is a non-zero, you can reject the data. So this is the process is given for that. So one simple example for you to understand this CRC process. So this is the CRC generator. It means that working under the center side. working under the center side. So here the message so what's the original message m is equal to given here is 1 0 0 1 0 0. This the original message is given. And what is the divisor d of x? So this is the divisor predefined binary number. Predefined binary number. So here it is given 1101. 1101. So count the number of bits for this divisor. So make it as a n. N is equal to 4. 4 bits are available here. Now make a message with n minus 1 number of zeros added to this message 1 0 0 1 0 0 and n minus 1 is 4 minus 1 is equal to 3. So you need to add 3 zeros. So this is the message what we are going to perform the division. So that you can see in the slide. So data plus extra zeros, that is 3 zeros are added. 3 zeros are added. So here you can perform the modulo 2 division. So 1 into 1101 is 1101. Perform the XOR operation. So performing the XOR operation 1 1. So as per I said the previous table. So 1 1 0 0. When both digits are similar digits, it gets a 0. When two different digits are have, it generates the 1. So 0 1 1 0 0 0 1 1 0. So the trailing 0 is always you have to neglect that. That is the last digit as per the division rule. That you know very well about that. As per the division rule, it can be rejected, this 0. So 1 0 0, then you can bring 1 0 from the message to your process. So now you get 4 digits 1 0 0 0. Then again 1 into 1101 1101, you get the result 1010. So this 0 can be, you can downwards to being the further process. So likewise each 0 you can put downwards to find your computation and you get that. And in one stage, sir, if you get the zeros like that 0 0 get, then how we can proceed? So the trailing zeros, that is the leftmost 0 only can be rejected, or we can escape from that. That is the dividend rule, divisor rule. So the other zeros can be considered. So this also be eliminated. So how can we eliminate? So for that you can add a 0 in the dividend part. That is quotient part. You can add a 0 and put all 4 bits are 0 and remove this 0 from the computation. Now you get 1100. And finally put 1 into 1101. You get the remainder as 001. So this remainder is generated. So this is called the CRC. So while adding the 0, what it says, when the leftmost bit of the remainder is 0, we must use 0000 instead of the original divisor, because we need to skip or eliminate from that 0 to the other message once, because AND or OFF, AND is come to process instead of the OFF. So OFF cannot be compute anything, so that we not consider to 0. So for eliminating this 0, we have to use this. So after generating this CRC, it can be added to the original message. So original message is 100 So the CRC is 100 the remainder is 001. So this remainder is added here. So the total thing is called CRC checksum data unit. CRC data unit. So this can be transmitted to the receiver side. So this is the whole technique what it is followed by the center side, that is the generator. Then checker, CRC checker, the receiver side, it can be use this message, that is the CRC message as a original message. So data plus CRC received. then the same predefined binary number divisor is used here, and we are processing the modulo to division what we perform in the center side. So the similar cases, so where we have the 0, we add 4 zeros to eliminate or to skip the 0 from the leftmost digit as a 0. Then finally, when it is the remainder is 0, this message is original message. When the remainder is, we get the other value other than 0, so it can be rejected, it is not a original data. So in this example, it is a original. Suppose if we added or any one bit is changed here, any one bit is changed here, automatically we get remainder here. So the received message is not a original message. So this can be explained in this CRC checker. So one more example is working here. So M value, that is the message value is 111011, and compute value is given, then G value is 1101, divisor value is given. So you can perform the division as like what it is there. So the remainder you are getting is 111, 111, 111 you are getting the remainder. So adding with the remainder to the original message 111011, we are getting the CRC value. Then the receiver side, the checker, CRC checker, we are having 1101 is a divisor, then 11011, 111. So this is the CRC with the original data. Then again we can perform the modulo division value. Finally we are getting the remainder as 0. Okay. So when we are getting the remainder as 0, there is no error is detected. When the remainder is viable, there some error is detected. Okay. So this process is given. When you take the practice on these problems, you can easily understand. Okay. Then the next thing is CRC polynomials. CRC polynomials. So here what we discuss about the binary numbers, binary digits, binary terms, binary words. So all this we can perform on this. Sir, suppose we have the message using the polynomials for x terms. So x squared plus 1. So how can you convert this as a binary terms? How you can perform the CRC for this? So this is also possible. Message can be computed using polynomials. So that it is given there. So the reason for this taking the polynomials is very simple. That is, it is too short. When you are performing, the binary digits are very high number of binary numbers, dot 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 0 1. So how many division you can take it there itself? Remember that, imagine that how many number of computations you need to perform in the division. Instead, when I am using these polynomials, with a few steps I can complete this process. With a few steps I can complete this process, so that we are saying it is too short. Then it can be used to prove the concept mathematically, because zeros and ones, it makes some confusions, or it looks like a signals or digitals. So but when you are using the x terms or polynomial terms, it is mathematical computation. You can prove through the mathematical also. That is usage of polynomials. So how we can convert that? What are the terms available? So the available terms are convert as a 1. So for example, here x squared is available, you can make it as a 1. So this is the leftmost highest exponential value, that is x term value. So here is 2. In that example we are using 7. Okay. So which term is not available? So after x squared we have x. So this term is not available in this equation. So you make it as a 0. So this is x power 1. And the last digit is x power 0. So this x power 0 is 1, because whatever the digit power 0 is equivalent to 1. For example, n power 0 is equal to 1, a power 0 is equal to 1. So likewise, x power 0 is equal to 1, y power 0 is equal to 1. So whatever the term power 0 is equal to 1, so that it is we have here. So x power 0 is available, x power 2, x power 1, then x power 0 is available, you can make it as a 1. So 1, 0, 1. The available terms should be make it as a 1, which terms not available make it as a 0. So let me come to this example and find whether the result value is correct or not. Tell me, what is that? So x7 is available, so you can make it as a 1. Then next you have x5. So what the value in between you have? x7, x5. So it is not a sequence terms. So in between, in these two terms between we have one term, that is x6. So that it is given here, x6, it is not available in this equation, so make it as 0. Then x5 is available, make it as 1. Then next term you have x square, that is x2. So here is a 5, here is a 2. So in between the two terms are missed. What are that? Yes, x4 and x3. So x power 4 is missed, you can make it as a 0, and x power 3, so that is also missed in this equation, make it as 0, and x squared you have here, make it as 1, x is available, you can make it as 1, x power 0, that is 1 is available, make it as 1. So the final conversion from this polynomial equation to binary number is 1 0 1 0 0 1 1 1. So likewise, if you have any examples with the polynomials, you can convert to this binary and perform the addition and you can find the value. So this is one way. First you can easily understand through this one. Then we can directly perform the CRC generation, CRC checker through the polynomials also. That example also available, we discuss. Okay. So here the polynomial checking. So how the CRC perform the polynomials. So if you are converting, see the data is x cube plus 1. So when you are converting 1 0 0 1. So the division, what is x cube plus x plus 1, 1 0 1 1 is given. So this is the predefined binary number divisor is given. Okay. So this divisor you can take it as here. So when you are performing the binary division 1 0 1 1, here 1 0 0 1, you can perform here. So it means that you can add 3 digits, 3 zeros here. Then you can perform 1 1 0 1 1. So this is 0, this is 0, this is 1, this is 0. So this is you can automatically eliminate as per the divisor rule. So you can eliminate this, and this digit you have 0. You can downwards 1 0 is you get the 0 for making the 4 bits, but here you have the 0. When we have the leftmost bit is a 0, it should be add a 4 zeros to eliminate this 0. So when you are adding these 4 zeros, the quotients also you can add a 0. So now you get the value, you can skip this, you can get 1 0 0. Then you can downwards here, you can get another 0, you can make a 1 1 0 1 1. So 0 0 1 1. So this can be eliminated. So you don't bother this bit. But again you have a 0 here. So what you can do? So this bit you can downwards 0 0 0 0. So here you can add a 0. So this can be eliminated 1 1 0. So this is the CRC can be generated. Right? So how many steps are involved here when you are performing the binary modular division? So at the same time, when you have the polynomial division here, I am taking only x cube plus x. So here x cube plus x plus 1. Okay. So here we are making x6. Right. So x cube plus 1, making this. So x cubed into x cube is a x6 plus x cube into x is equal to x4 plus x cube into 1 is equal to x cube. So this is performed here. So this x cube is added for that the number of zeros. X cube is added for the number of zeros. So here the 3 number of zeros can be added because 1, 2, 3, 4 digits are there. 4 digits are there, n minus 1, 3 zeros you have to add. So x cube you have to add it there. Okay. So while performing x6 is cancelled, then x4 is generated here. So for this you are getting x into x cube is x4, x squared plus, so x squared plus x is, so x squared plus x is 1, 1, 0, because there is no x power 0. So that's why we are generating 0. So this can be generated. So for generating this, we have these number of steps here, but in polynomial equation is just a matter of 2 steps. But while understanding this computation is very complex and difficult. So that's why the students are supposed to perform this kind of communication, binary division, so that you can easily understand and generate the CRC to understand that. But the computers or systems cannot use this kind of things because it's a time consuming process. So that the computer use the mathematical polynomial process. Okay. Then in computers they generally used, that is common standard polynomials. So CRC 8 used for ATM header and CRC 10 is used for ATM AL layer, and ITU 16 used for HDLC, then ITU 32 used for learns. It means that this is standard CRC computation process which is used for each application. For example, LAN, local area network. So what our institution we have, the laboratories are constructed with the local area networks. So in that local area networks, packets or messages are computed with the CRC 32 and HDLC layer. So this HDLC layer work with the MAC layer. So MAC sublayer is available for the data link layer. So that's so far we discussed the data link layer. So the layer 2, in the data link layer, the HDLC provide the linking procedures, linking protocols. So HDLC one of the linking protocol. So that the HDLC use the CRC generation and checker based on this CRC 16. So this polynomial is standardly and permanently used for this kind of applications. HDLC, in the sense it is used the CRC 16. And ATM AL. So ATM, it is not what you are using the ATM cards. It is not like that. So it is a high speed network, asynchronous transfer mode networks. So in this high speed network you have a one layer, that is ATM adaptation layer. So to perform that layer functionality you need to use this CRC 10. So this standard CRC you have to use it there. Then ATM header is another application. ATM network, we have the header information, that also we have the CRC. For that CRC you have to use CRC 8. So these kind of common polynomials or standard polynomials used permanently in the computer systems for different applications. So likewise also we can generate different applications. Okay. Let you take this example and try to work out. So frame is 110101111 and the generator is 10011. So using this you can find and whether the answer is correct or not. You work out with that and find it. Okay. Then CRC can detect all burst errors that affect an add number of bits. It means that add parity works there. CRC can detect all burst errors of length less than or equal to degree of the polynomial. So length based on the polynomial degree. So that what we discussed here, x square is 1, x1 is 0, 1 is. So the length of the polynomial can be used onto that. But so overall altogether is CRC is the best method to detect the errors. And the last technique is checksum, which is mostly used for the internet purpose, but here also you are using the similar process. So while I am saying the same concept you get bored. So let you understand what it is that it is. It's a similar process, but the only one change is that we are performing the sum. So for example, we have 4 data units, 1101, 10110, 11001. So likewise we have 3 single data units available. So while transmitting this data unit, you need a sum. You take the sum of this data units. So this is considered as a single data unit, and take a one complex one's complex complement. So this one's complement that you have studied in your digital principles, it means that interchanging of the bits. So instead of the 0 you can change as a 1, interchange of that is 1 is a 0. That is the one's complement. You make a one's complement of this sum and transfer to the net, so that it is given here. So section 1, section 2, section k, up to that you can make a sum of n bits and make a one's complement and pass it into the that. So the center side is that itself. Okay. See, 2 data units are available. Take a sum, and this sum can be, make it as a ones complement. Take it as a ones complement here. Ones are zeros, zeros are ones. That is a ones complement. So this data unit can be transferred into the net. Okay. So this is you are passing into that. So finally, the receiver side, it receives and perform all this and get the complement process. So the original data unit is passed there itself. So the simple process, the same again, the generation and checker process both happen in the center and receiver side. Okay. So up to this, let me stop here. The error correction we will discuss in the next seminar. That's all. Thank you.